Imagine standing in the engine control room of a massive LNG carrier. You know the type, those floating cities transporting liquefied natural gas across the ocean.
Yeah, they are absolute behemoths.
They really are. It's loud, it's vibrating, and somewhere deep in the belly of this beast is a row of steel cabinets that are literally keeping the ship alive.
You're talking about the 6.6 kV switchboard.
Exactly, the 6.6 kV switchboard. It is the beating heart of the vessel. But here's the thing that always blows my mind. How do you move that much electricity from a diesel generator to a massive cargo pump in a gas-filled zone without, melting the wires or causing a massive explosion?
It is a really high-stakes environment. And to understand it, we are not just guessing today. We're looking at the function description for 6.6 kV switchboards, ABB switchgear on board.
And this document is fascinating because it's not just a manual. It's a logic map. So our mission for this deep dive is to really trace the flow of current. We want to give you a step-by-step picture of how this works. We're going from the diesel generators all the way to the cargo sections, decoding the safety logic that prevents blackouts, and figuring out exactly what happens when things go wrong.
And trust me, on a ship this complex, the system is designed to assume things will go wrong eventually. The engineering is all about how you handle the failure, not just the success.
So let's start with the big picture. System. Give us the anatomy of this power grid. How is it physically laid out?
Right, so physically the system is divided into 4 main sections. You really have to banish the idea of a single grid like you have in your house. On Hull 1810, the 6.6 kV system is divided into 4 distinct geographical and electrical islands. You have your main switchboards, which are MSWBD1 and 2, and your cargo switchboards, CSWBD1 and 2.
Let's unpack that split. Main versus cargo. What is the actual difference in their jobs and why separate them?
Think of the main switchboards as the power plants. This is where your diesel generators, or DGs, feed in. On main switchboard 1, you've got generator 1 and 2. On main switchboard 2, you've got generator 3 and 4.
So they are generating all the juice.
Precisely. And these boards also power the critical stuff to move the ship, like the propulsion transformers and the bow thruster. They are the source.
Okay, so the main board is keeping the lights on and the propeller turning. What about the cargo boards?
The cargo switchboards are the heavy consumers. They don't generate power, they just eat it. They feed the massive cargo pumps, the spray pumps, the high-duty compressors, and the low-duty compressors.
So the cargo boards are like the hungry teenagers of the ship.
That's a great way to put it. And there's a very specific technical reason for this split. Those cargo pumps are huge inductive loads. Starting and stopping them creates massive spikes and dips, which we call harmonics.
Oh, electrical noise.
Exactly.
Yeah.
You do not want that electrical noise messing with your sensitive navigation radar or your propulsion control on the main board. So you isolate them in their own electronic room.
That makes perfect sense.
Okay,
so I want to visualize the journey of an electron here. I'm an electron created at diesel generator 1. Where do I go? Walk me through the path step by step.
All right, let's trace it. You start at the generator. You pass through the generator circuit breaker to get onto the main bus bar of main switchboard 1.
Okay, I'm on the main bus.
Now you're sitting there on the main bus. But to get to the cargo sections, to those pumps, you have to travel through what's called a transfer feeder.
A transfer feeder? That sounds like a bridge.
It is exactly a bridge. It connects the main switchboard to the cargo switchboard. But here is where the logic gets interesting. The system has strict rules about how these bridges operate. The document mentions a 2 out of 3 interlock rule regarding the transfer circuits.
We can't just open all the bridges at once or close them all willy-nilly.
Basically, yeah. Normally, the transfer breakers are closed, so power flows freely from main to cargo, but you have to be careful about paralleling. You can connect main 1 to main 2 to share the load. That's standard. But the logic strictly prevents you from connecting cargo switchboard 1 directly to cargo switchboard 2 unless the main switchboards are also connected.
Oh, I see. It forces the electricity to take a predictable path.
Exactly. It prevents you from creating a loop where power flows backward or in a circle, which could overload the tiebreaker. It forces the operator to keep the grid shape standard.
Okay, so we have a really clear flow now. Generator to main board, across the transfer bridge to the cargo board, and finally to the pump. But before we turn that pump on, I noticed something in the abbreviations and definitions section of the source.
Oh, about the power supplies.
Yeah, it lists a UPS and an emergency supply. It seems like the switchboard has its own nervous system completely separate from the 6.6 kV high voltage.
This is a crucial distinction that new engineers often miss. The switchboard needs to think. and it needs to act. And it uses two completely different low voltage power sources for that. Frankly, this is where rookie engineers get into serious trouble during a blackout.
Break that down for us. Thinking versus acting. What voltages are we actually talking about here?
The brain, or the thinking part of the switchboard, runs on 110V DC. This comes from an uninterruptible power supply, a UPS. This 110V DC powers all the control circuits and the protection relays, specifically the REM545 and REF543 units mentioned in the source.
Those are the computers basically watching the line.
Correct. And it is vital that they run on a UPS. Even if the entire ship goes black, total dead ship, the 110V DC keeps the brain alive so it can tell you why the ship went black. It powers the memory, the logic, the alarms.
So the brain is 110V DC. What about the muscle?
The muscle runs on 230 DC. This comes from the emergency distribution system. This powers the heaters, the internal lighting, but most importantly, it powers the spring charging motors inside the circuit breakers.
Spring charging motors? Wait, why does a breaker need a motor?
A high voltage breaker doesn't just click on like a light switch in your living room. It uses a powerful mechanical spring to snap the heavy contacts shut or rip them open instantly. That spring needs to be compressed or charged.
And the motor does that.
Exactly. We use a small electric motor to wind it up, and that motor needs 230V AC to run.
So let me paint a scenario. I have a blackout. I've lost my main generators. I still have my 110V DC from the UPS, so my computers are on. But I've lost my 230V AC because maybe the emergency generator hasn't kicked in yet.
In that specific window, you are paralyzed. You could see the breakers on the screen. The brain is working, but you cannot close them remotely. The springs are discharged, and you have no AC motor to wind them up. You would physically have to go to the breaker and pump a handle to charge it manually.
And on a ship with 40 breakers, you absolutely do not want to be doing that in the dark.
No, you don't. That 230V AC is the muscle that allows the system to reset itself automatically. If you lose the AC, you lose the ability to act. But if you lose the 110V DC, the brain, the breaker, trips immediately.
Why does it trip if it loses DC?
Because without its brain, the breaker is blind. It doesn't know if there is a massive fault happening or not, so the ultimate failsafe is to open the circuit. Safety first.
That is a fantastic detail to pull out of this document. Now, speaking of breakers, the source material makes a really specific distinction between the actual hardware used. It talks about CBs and VCs, circuit breakers versus vacuum contactors. Why do we need two different types of switches? Why not just use one type for the whole board?
This is all about the heavy artillery versus the marathon runner.
I love an analogy. Run with it.
The circuit breakers, specifically the VD4 type mentioned in the manual, are the heavy artillery. They're used for the generators, the transformers, and those transfer feeders we talked about. Their primary job is to be able to break massive short circuit currents.
Meaning if something goes really wrong.
Right. If two wires touch on the main bus and current spikes to thousands of amps, the VD4 can blast that connection open safely and quench the resulting arc. It's built for raw stopping power.
Okay, so that is for the main power flow, the heavy defense. What about the vacuum contactors?
The vacuum contactors, or V-contact type, are the marathon runners. These are used for the motors, specifically the cargo pumps and ballast pumps. Think about offloading LNG. You might start and stop a cargo pump dozens of times in a day. Start, stop, start, stop.
And a circuit breaker can't handle that.
A heavy circuit breaker isn't designed for that kind of frequent switching. The heavy mechanical parts would wear out way too fast. A vacuum contactor is much lighter, built to switch on and off constantly without wearing down.
Well, it is a catch, right?
Well,
I see fuses mentioned right next to the contactors in the schematics.
It's a huge catch. A vacuum contactor is great at switching normal loads, but it is terrible at breaking a massive short circuit. It just isn't strong enough. If a wrench falls across the terminals at the pump, the contactor cannot open fast enough or strong enough to stop the explosion. It might actually weld itself shut trying to break that current.
So the fuses are essentially the bodyguard for the contactor.
Exactly. That is why cargo pump starters always include fuses. If a massive short circuit happens, the fuses blow instantly to cut the power. This protects the contactor from fusing shut and saves the system.